This is a curious question. It says prove that 2n squared plus 5 is a prime number for various values of n. It might as well say show. We are proving it, but it's illustrating a part of the syllabus called proof by exhaustion, and it's a bit tedious as a question, really, but there we are. We have to be able to do these things. So 2n squared plus 5, well, when n is 1, we get 2 times 1 squared plus 5. When n is 2, we get 2 times 2 squared plus 5. When n is 3, we get 2 times 3 squared plus 5. And when n is 4, we get 2 times 4 squared plus 5. And we can work these out fairly easily. You can use your calculator if you must, but 1 squared is 1, times 2 is 2, plus 5 is 7. 2 squared is 4, times 2 is 8, plus 5 is 13. 3 squared is 9, times 2 is 18, plus 5 is 23. And 4 squared is 16, times 2 is 32, plus 5 is 37. Then we must make sure we state that these are prime numbers. So I can write this mathematically by saying these are members of the set of prime numbers. So that's a special P with an extra upright. And we might then write as well, therefore the statement is true. So, why did they stop at 4? This is going beyond the question now. We've done the question. So, what would happen if n were 5? Well, you could work it out, or you could think, if n is 5, we have 2 times 5 squared plus 5, and we might be able to see that 5 is a factor there. So 2 times 5 squared, if we take a 5 out, leaves us with 2 times 5, and 5 itself leaves us with a 1. So that proves that in the case of n equals 5, 2n squared plus 5 is not a prime number, if we needed to show that. We don't actually have to find out what the final number is, nor do we care if we're just testing whether it's a prime number or not. What is interesting about this question is it's related to prime numbers, and it's giving a formula that gives us prime numbers, albeit for a very small number of values. Now, you can research prime numbers and find out if there are any formulae that give us all the prime numbers. So I'll leave that as something for you to have a go at. But the important thing is that you understand that prime numbers are important because they're the building blocks for numbers. So they're also important in lots of areas, as I'm sure you will know, and they've become increasingly important in the computer age with regards to cryptography. And there's a video in our Year 13 bridging session videos, which you can find on YouTube, about number theory and internet security, which you may find interesting. So prime numbers are important, and if we could generate prime numbers, that would be handy. One formula that has been used is Euler's formula for prime numbers, and it is n squared plus n plus 41. Now, we can have a look at the first few values of this. You could type into your calculator, but a quick way of doing it is to use an Excel spreadsheet. And so we have the column A is the values of n, and column B is n squared plus n plus 41. And for those of you who are interested, you probably already know how to do this, but that's the formula that we've used to generate these numbers. And there's a fair chance you'll recognise that these numbers are prime numbers. So it certainly works up until n equals 10. Now we can drag our Excel spreadsheet further down, we can drag these two cells here if we selected them and then drag down, and it will carry this on for us. But what would be interesting is if you can look at the formula and think of a number where it's not going to work. And it's not immediately obvious, so you might want to pause and have a think about that. Okay, maybe you found a number that stops it from working. Maybe you haven't. But what we certainly can do with this is we can say that n squared plus n plus 41 equals n times n plus 1 plus 41. And then, in a similar way to the way that I showed you that 2n squared plus 5 doesn't work when n is 5, because we can see that 5 is going to be a factor of both bits, we can see here that if n was 41, we would have 41 times 42 plus 41, which is 41 times 42 plus 1, and therefore not prime. So we can see that this formula breaks down when n is 41. Of course, it may be that it's not true for some n smaller than 41 as well, but we have at least proven that this formula does not generate only prime numbers. We can therefore say that we've disproven the idea that n squared plus n plus 41 generates only prime numbers by counterexample. So that's just a little look at some thoughts that come out of this question. So hopefully it's made this a little more interesting.